Welcome back. So moving on to section 13.2, we're going to be talking about length and area. So to start off talking about length, which is like a one-dimensional measurement, we're going to be looking at the distance between 2 points. And if I have 2 points, I want to think of them kind of as between any 2 points, I can make it a line. And so I think of them lying on a real number line. And so P, the point big P, corresponds to some real number little p. And point big Q corresponds to some real number little q. Okay, and then in that case, the distance between P and Q, which we denote with just putting those 2 points next to each other, capital P, capital Q, is the real number obtained by the non-negative distance of P and Q. So one way to write that is the absolute value of P minus Q, which is the same thing as the absolute value of Q minus P. So taking their difference and making it positive. Okay, so to look at a quick example, we have 3 points, P, Q, and R on a real line. P corresponds to negative 4.628, Q corresponds to 18.75, and R corresponds to 27.5941. And we want to compute these 3 distances. So PQ is going to be, we can take it as P, which is negative 4.628 minus the 18.75. That'll give us a negative value, so we're just going to switch the order, which is the same as taking the absolute value of the negative 4.628 minus 18.75. So we should get the same thing either by switching the order here or taking the absolute value. And this gives us 23.378. Now looking at QR, again, we're going to take the bigger of the 2 points so that we get a positive length here. So that is 27.5941, and we're going to subtract off R, which is the smaller of the 2, which is, or I'm sorry, we're subtracting off Q, which is the smaller of the 2, which is 18.75. And we get 8.8441 is the distance between those 2 points. And then PR, we will take R first, which is 27.5941, and subtract off the negative 4.628. So that gives us 32.2221. So there's a couple things that we can notice from these distances. So one that I kind of just mentioned was that PQ is equal to QP, the distance between 2 points. It doesn't matter what order we take them because we're taking this absolute value. Another property that we can notice from this example is that if I look at this real number line, we have that P is around negative 4.628. Move it here a little bit. And then Q is kind of the next point, and R is the last point here at 27.59. And what we can see if we were to do out the sum is that the distance between P and Q plus the distance between Q and R should be the same as the distance between P and R. And so that means if I add these 2 distances, I get this. So if I add this 23.378 and 8.8441, I should get 32.221. And that's what this third property says. If I take the distance between P and Q and add the distance between Q and R, I should get the distance between P and R. So we can see that in our example above. The last little property, which actually I listed first, is just that the distance between 0 and 1 is 1 unit, and it's called the unit distance. Okay, so this is how we think about the distance between 2 points. And then to continue on with this notion of length, I can, if I'm thinking about a two-dimensional figure, so like a square or a triangle or a circle, the corresponding notion of length would correspond to the perimeter of that figure, or the perimeter of that polygon. So the perimeter of a polygon is the sum of the length of all of the sides. And so your book has this nice table which lists out the different figures, like a square with side length s, or a rhombus with side length s. The perimeter is just going to be the sum of all 4 of those s's. So that perimeter is just 4s. Since for both a rhombus and a square, the side length is the same for each one of the 4 sides. And then for a rectangle, parallelogram, and kite, it's going to be 2 times the length plus 2 times the width, or 2a plus 2b for side lengths a and b. Okay, and so looking at an example, or a couple examples, if I have a triangle and it has side lengths 5 centimeters, 7 centimeters, and 9 centimeters, to take the perimeter, I just need to add up those 3 side lengths. And notice here I'm just adding these side lengths, so I'm adding a certain number of centimeters, so 5 centimeters, 7 centimeters, and 9 centimeters, so my units should still be in centimeters. For the perimeter of a square with side length 8, so we could compute this by adding 8 to itself 4 times. Of course, that's the same thing as taking 4 times 8, like our formula above tells us, and that is just 32. And since, again, these side lengths are taken in feet, that's just 32 feet. Okay. So we talk about the perimeter for any polygon, like said, squares, triangles, rhombuses, trapezoids, and so on, to be the length of the sides. We have a corresponding notion for a circle. I guess it's up to debate on whether or not you think a circle has sides. This made me laugh because my son has this toy and there's like a circle, a triangle, and a square on it, and it sings these little songs when you hit them. And the one for the circle, my husband and I like debate about, because it says, a circle has no corners, a circle has no sides. This circle is round with an A inside, or something like that. But every time we're just like, does a circle have no sides? I'm not sure. Anyway, up to debate. So whatever we call the length of that one side, or however you want to say it, the perimeter of the circle would be the circumference. So you could measure the perimeter of a circle by just like taking one of those maybe cloth measuring tapes you would use in sewing and wrapping it around the circle and getting some particular length. That would be our circumference. And the thing we would notice is that the length of that length that you would get, the circumference, if I take it in ratio with the diameter of that circle, so I'm thinking of my circle, and the diameter is this line that goes straight through the center. And the ratio of this whole circumference to the diameter is always constant, and that constant is pi. So that's actually where the number pi comes from. That's irrational number. And so this is where we get this way of finding the circumference of a circle from the diameter. So the circumference is just pi times d, or in other words, since the diameter is 2 times the radius, so the diameter is equal to 2r. This gives me the circumference is pi times 2r, or c is equal to 2 pi r, which is maybe the more usual form that you would see the circumference of the circle in. Great, so that's where this comes from. It comes from this constant ratio between the circumference and the diameter that always occurs. Okay, so when we were talking about length, we're talking about this one-dimensional measurement. When we talk about area, we're now bumping up to 2-dimension. And so we're going to talk about how to get the area for a variety of different figures and shapes. So we talked about area when we were talking about units. And so we can imagine that if we have the area of a rectangle, we want to think of filling it in with a bunch of square units. So for example, if I take a 1 unit by 1 unit square, which is like my little grid here, and I want to fill in this rectangle with 1 unit by 1 unit squares, I would see that it would take 12 different squares to do so. And so this is this figure, this rectangle is 12 square units. And we can see that this corresponds to how we visually represented multiplication, because this side length is at length 4 units. And this side length is 3 units. And 3 times 4 is 12. So, so this is where we're getting our area for the rectangle is the length times the width. Whichever way you want to orient them. Okay, and then of course, for a square, the length is equal to the width, and so the area is just the length squared, or the side length squared. If you want to denote it with an S, of course, whatever notation you like to use is fine. Okay, so then to get the area for a triangle, it's a little bit more complicated. But the way we want to do it is we want to use what we already know, which is the area for a rectangle. So let's say I have this triangle. I'm going to start off with my representation being a right triangle, like I have over here. And let's now take another copy of this triangle to turn it into, oops, that didn't work out, to turn it into a rectangle. So I'm going to just kind of fill the rest of this out so it is a rectangle. It's not an exact rectangle, hard to do perfectly, but hopefully you get the idea. Okay, so I have 2 copies of this one triangle to get one rectangle. And then I know that the area of the rectangle is going to be h times b, right? Because it's the length times the width. And since we can see from the picture that this triangle is half the area of the entire rectangle, so the area of the triangle is going to be 1/2 that base times the height, or b times h. So this is clear for a right triangle like this one. It's a little less clear when my triangle isn't a right triangle. So I wanted to show how this works out in a more general case for some scaling like non-right triangle. So let's say we have this triangle, A, B, and C. And what we want to do is let's break it into two small right triangles. And so it doesn't particularly matter which way that I do this, but since mine is oriented this way, I'm going to, oops, that's not what I meant to do. I'm going to draw a nice vertical line through B so that when it hits this line AC, I form, it's like a perpendicular line to the side AC. Okay, so when I do this, I'm splitting up this base into R and S, these two lengths. So my base is really R plus S. Okay, and I'm going to call this height H. So my area of my triangle ABC here is going to be, well, I already know the formula works out for these right triangles. So for this triangle here on the left, the area of this triangle is 1/2 R times H, and the area of the triangle on the right is 1/2 S times H. And now if I factor out the 1/2 and the H, this is 1/2 R plus S times H. We already said that R plus S is the base. Great, so that's where this general form comes from. Great, so it even works with these non-right triangles was kind of the point of this demonstration. And the other point is that it doesn't particularly matter if I were to have bisected the angle B to form something that's perpendicular to this side AC, or if I reoriented my reoriented my triangle and used a right angle to bisect to form a perpendicular line with BC or with AB. Okay, so it doesn't matter which leg I take that height on, but the height does need to come off of the base is really the point. So the relationship between the base and the height matters, but which one is the base and which one is the height doesn't particularly matter. Okay, moving on to talking about the area of a parallelogram. What we want to use is the areas of objects we already know. So for a general parallelogram, we may not have 4 right angles. And so we can't use the area of a rectangle, but what we can use is the area of triangles. So what I want to do is first create, turn this parallelogram into 2 equal triangles, and then find the area of each of these triangles. And so the area of the parallelogram ABCD is going to be equal to the area of the triangle ABD plus the area of the triangle BCD. So to find the area of the triangle ABD here, we need this base, and we need this height. So then for this area, this is going to be 1/2 times the base times the height. And then what we notice is that this triangle ABD is actually the same size as this triangle BDC. And so for the area of the triangle BDC or BCD, this is going to be also 1/2 base times height. So we can kind of see that if we wanted to. These two heights should be the same, and that side B should be the same length as that side B. And so when I add these two things together, I just get the base times the height. So the area is equal to it's just base times height, not 1/2 base times height. Great. In the case of a trapezoid, we want to do a similar thing where we're going to break this up into triangles. So let's again take one of these diagonals. And so let's find the area of the triangle PRS, oops, and the area of the triangle PQR. So let's see, to get the area of this first triangle, PRS, let's call this side length A, and we're going to want to use this height H. And so this is 1/2 A times H. And then for the second triangle, we can notice that H will be the same, the height's going to be the same, but our base is going to be a different length. So if my height would be this height here, which is going to be the same as my other H, but my base is going to be this length B. So we have 1/2 B times H. So again, just factoring out the 1/2 and the H, this is 1/2 A plus B H. So the area. So adding the two parallel bases together is what this A plus B is. And then the height is the height between those two bases. Okay, so to put this in action, let's look at this trapezoid here. So notice we're given base heights for these two parallel sides. This is length 13 and this is length 6. And we're also given the height between them, the distance between them, which is 4. And so my area is equal to 1/2 6 plus 13 times the height. So 1/2 the sum of the bases times the height, which is 4. And so that should be 2 times 19, or 38 square units, or units squared, or whatever our unit is. Okay. Great. So looking at the circle, actually to do a rigorous verification of the area of a circle involves calculus. So what we're going to do instead is to approximate it using other shapes. So before we could use other shapes to find the exact area of these figures, here we're going to approximate. And what we're going to use is an octagon. And that may not seem super intuitive because we haven't talked about octagons yet, but let's see, but hopefully we'll see how we can do that when we draw things out. So the reason I'm going to use an octagon is because it looks really cool. It's a really close approximation of a circle. So basically, I'm just going to create my sides, my octagon, and I can see once I draw this on here that the area of this blue octagon figure is not going to be that far off of the area of the circle. So let's see here. So this is an octagon, right? 1, 2, 3, 4, 5, 6, 7, 8 sides. You might notice we can get a better approximation if we use more sides. So instead of an 8-sided figure, a 10-sided figure, or a 20-sided figure, or a 100-sided figure would give us a better approximation. And basically that's the idea of what calculus does here to rigorously justify the definition of the area of a circle. But we're not going to go into that much detail. We're just going to use what is a pretty good approximation. And you might say, I don't know the area of an octagon, but it's really easy to find the area of this octagon, just breaking it up again using triangles in this case. So for this octagon, I am going to I found the center of my circle here. I created a little isosceles triangle, and I'm going to find the area of this triangle, and I'm going to multiply it by 8, since there's 8 of these little triangles in here that we can see, sort of like summing up the area of all of these pizza slices. Okay, so the area of the octagon is going to be 8 times the area of the triangle, of one of these triangles. And so let's find the area of one of these triangles. I'm going to zoom in a little bit just to get a little bit better visual on this triangle. So I need the height, and that height, notice, is exactly going to be the radius of the circle. And I also need the base, which is the side length of this octagon. So the area of this triangle should be 1/2 times r times s. And just rewriting this, that's 1/2 r times 8s. And the thing to notice here is that this 8s is going to be the perimeter of the octagon, right? Because each of the side lengths was length s here. So if I just add them all up, that gives me the perimeter of the octagon. So this gives me reason to expect that the area of the circle might be 1/2 r times the perimeter of the circle. Or in other words, since we don't use the word perimeter to talk about that length of the side of the circle, circumference. Great. So we're just substituting that perimeter of the octagon with the circumference of the circle, since the circumference is basically the perimeter of the circle. And remember, our circumference is 2 pi r. And so if we go ahead and plug this in, that gives me 1/2 r times 2 pi r. And if I simplify, that is pi r squared is my area of my circle, which is exactly what we hoped it would be. Great. And so just to reiterate, we're kind of making a theory based off an approximation, but this can be done more rigorously by taking more and more sides of that blue figure and getting what's not an approximation, but an exact value. Okay. So here's an example of kind of putting some of these things together. So we have the dimensions of a standard key for a basketball court. And so we have kind of a rectangle with a semicircle plopped on top, and we just want to know how many square feet is in this key. So basically they're asking for the area, right? So what is the area of this key? And so let's break this up based on the dimensions that we're given. So it looks like we have a rectangle that is 19 by 12 feet. And then we have this circle that is plopped on top. And so if the length of this whole side here is 12, then half of it is 6, right? So that should be, notice that's going to be the radius of this semicircle. So I believe we have all of the things that we needed. So the area of the rectangle is going to be 12 times 19, or 12 feet times 19 feet. I'll write that out this way, using this kind of like dimensional analysis way of figuring out our units. We get 228 feet squared. And then the area of the semicircle Well, it's not going to be the whole area of the circle because we just have half of a circle, so I'm going to multiply it by 1/2, and it's going to be pi times r squared, and r is 6 feet. Okay, so this is 1/2 pi times 36 feet squared, which is 18 pi feet squared. And since this unit involves pi, but the other one doesn't, I'm going to just multiply 18 by pi, or approximately 3.14, and this is 56.5 feet approximately. So the total area, if I add these two together, is going to be 228 feet squared plus 56.5 feet squared. And so that should be 284.5 feet squared. Great. So I believe the last thing I want to talk about in this section is just the Pythagorean theorem. And the reason is we've kind of briefly touched on the Pythagorean theorem, but a way of justifying the Pythagorean theorem is through areas. So remember what the Pythagorean theorem says is if we have a right triangle and these two legs are length A and B, then, oops, I wrote it wrong. Then, little typo on here, then A squared plus B squared is equal to C squared. So the sum of those two lengths squared is equal to the square of a hypotenuse. And one visual way of there's a bunch of different ways we can prove this theorem, but what's really nice is there's a nice visual proof. So first off, in looking at this image and seeing how it's a proof, what we're going to do is just notice I have two rectangles that are exactly the same size, right? I've just copied them on grid paper, so it's very clear to see that they're the same size. These two squares, they're squares, right? And then what I've done is that you can imagine I've taken this little right triangle, or any right triangle, this blue right triangle, and I've made 4 copies of this exact same triangle in here by just kind of taking these little diagonals that match up nicely. So this area is the same as this area. There's these is the same as this area, right? So so again, this right triangle, this side length is A, this side length is B, my hypotenuse length is C for each one of these, right? So this side length is B, this side length is A. So the whole side length of this square is A plus B. This is A plus B, A plus B, A plus B, right? And the thing to notice is that then this white area on the inside should be C squared, right? Because the length of each of these sides of this blue square and this white square, I guess, in the center with a blue outline is going to be C squared, okay? So now I look at this square, this whole picture, and all I'm going to do is I'm going to pick up these 1, 2, 3, 4 triangles. I'm picking them up and I'm just going to move their location inside this the bigger square. And so when I do that, I'm moving these, I'm taking these two and I'm going to move them over here. I take these two and I'm going to move them over here. And so the white area that I'm left with should be exactly the same, right? Because it's just this big square with the area of these 4 triangles removed, right? So this white area, these 2 white areas should be the same as this white area. And now the thing to notice is the way that I've labeled them or laid them out is that, well, this short length was length A and this short length was length A. So the area of this small white region should be A squared. And this short length was length B and this length was length B. So the area of this bigger white square should be B squared. So the area of these 2 squares should be exactly the same as the area of this one white square in the left-hand thing, since all I did was move around where those blue triangles were located. And so this is my visual proof that this area of this white square here, oops, this white square here is c squared, and of these two squares here is a squared plus b squared. And they should be exactly the same because all that I did was I moved around the location of those blue triangles of the same size. Great. So this is really nice. You can actually do this out using a piece of paper and cutting up a couple triangles and actually make, I think it's maybe a more impactful argument when you kind of actually move things around, but this is a nice argument that you can use to show, your students why the Pythagorean theorem works. Okay, so employing this in a new way, we've talked about, we've used the Pythagorean theorem before. So we can use this to construct line segments of irrational length. So the square root of 13 is an irrational number, right? Because 13 is a prime and we're taking the square root of a prime. So the way I would do this is I noticed that 13 is equal to 4 plus 9. And 4 is just 2 squared, and 9 is 3 squared. So I want to take a triangle with side lengths 2 and 3. So if I take one of length 2 and one of length 3, so this is length 2 and 3, and I make this a right triangle, then this hypotenuse side should be length 13. So this means that C should equal the square root of 13. Okay, so we can use this to construct this irrational number. So the construction, kind of the answer is really just this line segment. I don't know how to circle that, so I'll leave it here. Great. And then one last concept I wanted to touch on is the triangle inequality, which is very intuitive. And it says basically if I have 3 points, P, Q, and R, that the length between P and Q plus the length between Q and R has to be bigger than or equal to the length between P and R. And so you can notice this just by visually looking at this. This is why it's called the triangle inequality. But this triangle that we drew was if Q happened to be moved onto P and R, then these two, then PQ plus QR is exactly the same. But for any 3 points in space, if it's off of this line, notice that PQ plus QR is definitely going to be longer than this length PR. Okay, it's kind of a visual explanation of this triangle inequality. So I'll end here by just mentioning a couple of exercises that you might want to look at and talk to me about at the end of this section. So again, one is about doubling length versus doubling area, number 53 at the end of the section, and number 55 here is touching on what we talked about when we were talking about the area of the triangle, which is whether it matters kind of what we take as the base and the height. And so those are 2 good exercises to work on.